All right. So, hello everyone. I'm John DeGoes. Welcome to FP to the Min. So before I begin today, I want to thank a few people. First off, I want to thank Signify Technology, not only for the invitation to close this conference, but for working extremely hard to put together what has been an amazing lineup of 13 talks, well, 12 if you don't count mine. Hopefully mine will not be half bad too. Anyway, working so hard to put this conference together. This is a free conference, and I know that everyone at Signify worked really hard. So thank you to Shannon and Ryan and Mitchell and Ellie and all the other people who are behind the scenes working to make this happen. Also, thank you to the attendees of Scala in the City conference for coming and sharing in this day to celebrate the Scala programming language and functional programming. And an extra special thanks to those of you who were able to chip in and donate, because I think we've raised nearly 10,000 euros for COVID-19 relief efforts all around the world, which is just amazing, especially considering all of this was put together in the past 4 weeks. So I am going to open up the chat here, and that means I can see your comments. So if you want to heckle, and there will be live coding, so please, by all means, heckle. I will be able to see that, if not necessarily respond to that in the Zoom webinar chat. So please open that window up. The story for this talk actually begins about 2 years ago when a friend of mine, Ollie Mahazoiva, I hope I got that right, Ollie, otherwise known as Ollie Kitty, perhaps because her last name is almost impossible to pronounce, at least for an American like me, invited me to do a talk on one of her podcasts. And I gave her a choice. I said, look, I can do functional data modeling for you, or I can take a little snippet of procedural code and I can dial up the FP all the way to the max, way beyond the max. And so she thought about it for a couple days, and she got back to me and she said, well, everyone I talked to says do FP to the max. And so I did it. And I think 25,000 views later, the video has had an impact on the Scala community. And even though I started off that talk with a disclaimer saying, hey, please don't try this at home, thousands and thousands of people went and they tried it at home. And some good came out of that. First off, so a lot of people in that talk, they were able to see that even the very esoteric aspects of functional programming, even the very super fancy stuff, it actually does have practical, real world applications for programming in the large. And that's the amazing thing. That video, it helped FP click for a lot of people. A lot of people get FP in the small. That video helped it click for FP in the large. The bad thing is, because so many went and tried something, and I said, please don't try when you're at home, I had a lot of comments saying that, you know, this is interesting from a theoretical academic perspective, but there's a lot to digest here. And if I were to teach this to my team, they would laugh at me. They would laugh me out of my job. And so ever since then, that was 2 years ago, ever since then, I've slowly, bit by bit, come around to understand that point of view. And I think that in the past 2 years, the functional Scala community has found easier ways to do a lot of what I showed people to do back then. Basically, to get a lot of the benefit for a fraction of the cost. And so fast forward to today, when I look back at that video and, you know, sometimes make fun of myself for just the way that sort of rolled out. I think now is the time to give another talk that has the same purpose, more or less. This talk is to help you understand functional programming in the large. It's to help you get the big picture of FP, but it's to do it in a way that is going to be way more accessible than that preceding talk. And in particular, in that first video, actually, I can open up some of the code and show you. I've got it here loaded up. I can open up this code in this video. My goal in this talk is to basically give you almost all of the value, but without any of the type classes that you see here. So there's lots of type classes inside the FP to the max series, without any implicits. So there's tons of implicits everywhere here, without any higher kind of types. There's lots of higher kind of types here. And then without any jargon that some find scary from category theory. So basically give you the good, hopefully as much of the good as I can anyway, without any of the bad. And my goal is, my sort of overarching goal here is to help you, is to basically instill in you a vision for how functional Scala can make you a very productive and extraordinarily powerful and also hopefully joyful programmer, because some of the stuff we talked about last time in FB to the max was not necessarily all that joyful. There was a lot of boilerplate involved. Okay, so with that extended introduction out of the way, let's go ahead and jump into FP to the min. Just rearrange some windows here. All right, so here's the setup for this problem. We are given this chunk of code base, and what it does roughly is it downloads data files from the internet, actually using GitHub. It downloads them from GitHub, and then it parses them into CSV files, and it goes through and it does a bunch of aggregations. So it does filtering and reductions and aggregations, and it does this over a whole bunch of different data sets. And this program runs at regular intervals. So it does this entire process from beginning to end at regular intervals, 1 minute in length. And then at the very end, it dumps out a bunch of statistics that it got from the last round of running. And you can see the source code will be online shortly, but for now, I'll just give you a high level walkthrough of this code base. So the main entry point is this stats collector thing. And this is where the business logic of this application resides. So the main function, it creates a bunch of services. It creates a scheduling service, which will be used for repeating this at regular intervals. It creates this COVID-19 service, which is utilized to download COVID-19 data sets from GitHub. And it requires a GitHub service, which is created here. Then it goes ahead and schedules this using a scheduled executor, which is something you'll find in Java, and runs this aggregate and summarize basically one time every minute, with the exception of the first time it runs without delay. And this, at the very end, it basically waits for you to enter some line of input, and then it tries to cancel this schedule and it shuts down. The aggregate and summarize, what it does is it first calls the aggregate function, which is responsible for downloading all the different data sets and slicing and dicing and aggregating them over the course of a month. The specific month we're looking at here is April. And then it truncates those results after performing the aggregation to only show really the top 10. And then it prints out the summary along with this little message, which is also repeated in this scheduled loop. So you'll know that you can end the program at any time by hitting enter. So the aggregate function, it's written up here, and it's just very simple business logic. Most of the heavy lifting is actually inside this CSV module. What it does is it computes the number of days in the current month, or rather in the specified month, and then it loops through all of those days, mapping every single day into a CSV file. And this CSV file comes from loading the data for this specific month and this specific day in that month. And then it's going to do some processing on the CSV file. It's going to delete a bunch of columns that it doesn't need. Then it's going to group this data by the province, state, and country region to perform roll-ups on all the remaining fields that are not specified in the group by. So we're going to do an aggregation by province, state, and country region. And then when we're done, we go ahead and sort by the reverse of the desk field converted to an int. So in the end, we're going to see something that looks like this. Let me actually show you the output so you can get a sense for what this program does. Assuming it runs. All right, here we go. It just takes a little while because it's got to download 20 some days worth of data, and it's got to aggregate them all. So that takes some time, but then we'll just let it run one time. You can see we get back the results we expect, which is this is basically COVID-19 data for way back in April. It was only a month ago, really, but it feels like a totally different world since then. Anyway, so that's what this does. And then at the very end here, you can see it does a reduction of all these data sets. So because this is happening for every single day of the month, all of these different days, the aggregation of all these days need to be combined, and it's combined using this plus operator on the CSV, which just smashes everything together to get back the totals. All right, so what we're going to do now is take a look at some challenges associated with this project. These are going to be some issues. Some of them are bugs actually that are known about in this application, and others are more feature requests, and deciding which and which is a little bit difficult, so I just grouped them all into one group here. As you can see, number one, this application leaks file descriptors and eventually stops working. So you run this for a while and it goes along fine for some period of time, and then it just stops. So it's running out of file descriptors, which means there's a resource leak in this application. So one of the things we're going to try to do is explore how using functional programming can help us deal with resource leaks. Number two, if some days worth of data is missing, no statistics will ever be collected. Okay, so this is interesting. So for example, if we were to run it on the current month, which has incomplete data, then apparently this program won't produce any output at all, ever. So there's some problem there that we'll have to look into. And more likely than not, that's around error management. And we'll see how functional programming can help us reason about error management in applications. Number three, if the application is sensitive, or rather, the application is sensitive to transient problems in the GitHub API. What this one means is that sometimes GitHub API might be a little flaky, or we might have, like the laptop might be experiencing connection difficulties or whatever. And in this case, the program just stops working. Even if retrying a few moments later would have succeeded, the application just stops. So it's not very robust. This is a robustness problem that's connected to error management. So we'll take a look at that. Number four, the application, this is more like a feature request. Basically, this takes a really long time to crunch all these numbers. People want results faster. So this application should download and aggregate all these data files in parallel. Okay, so we'll see how functional programming can assist us writing concurrent and parallel applications. Number five, the application should support a timeout on file downloads so it doesn't hang forever. Okay, so one time this application got stuck. And it got stuck because a file download was taking a huge amount of time, or a socket wasn't closed even though the server wasn't sending any data. And so the application was just hanging for an indefinite amount of time. And we'll see if we can use functional programming to solve that problem. And then finally, if the application is still downloading the files from a previous run, it should not start a new run. So there's a separate problem here that looks like if it spun up and it was starting to download the files, but for some reason it took more than a minute to download those files, then it started downloading those files again. And so you can imagine that in that situation, the computer might get slower and slower and slower as it's trying to aggregate and download, and it gets more and more behind, and eventually the program runs out of memory and things crash. So there's lots of problems with this application. Let's go ahead and take a look at this. And what we're going to do is we're going to focus on number one, and we'll definitely fix that. And then hopefully we'll have time to fix number 2 through 6 as well. And fixing number 1 is actually, we're going to tweak the architecture of the application. We're going to start tweaking it to be more functional. You've heard a lot about functional programming today, beginning with WM's keynote on ZIO and pure functions, and hopefully you attended that or have that background in your mind. So I'm going to assume some of that background knowledge today. I won't be precisely reviewing what it means to do functional programming, but we are going to take this application and bit by bit, step by step, we are going to refactor it. And we're going to try to make it more functional. And we're going to see how functional programming enables us to solve all of the different bugs in this application, as well as add these features in a principled way that makes us very productive and also is actually quite pleasant to use. So digging into Stat Collector again, let's take a look at this. And everyone in the world has been asking for larger font sizes, so I'm going to bump this up a bit. Hopefully you can all see that. All right, so here we are, aggregate. And this is the function that aggregates a month worth of data using the COVID-19 service. And we know that according to this problem description, it's leaking file descriptors and eventually stops working. So here, the only thing you can see related to I/O is this unsafe load. Well, unsafe load presumably loads this data from GitHub. So let's drill down in there and see if we might be able to find the problem. Okay, well, unsafe load is just a reference to this COVID-19 interface. This is an interface, and this interface is useful because it allows us to code to the interface and not the implementation, which can help us write better unit tests. So we look in here and we see the implementation is in this class called live, and we see the unsafe load. And what unsafe load does is it calls CSV from string, so it parses into a CSV file the result of downloading some data from GitHub using the unsafe download API. So let's drill down there and see what we see. Okay, so GitHub service. This is the GitHub service, and we see the unsafe download here, and it takes a GitHub slug and a file on that repository, and it gives us back the contents as a string. And what this one does is it's implemented by calling unsafe open with slug and file, and then it calls getlines on that, and then it calls makestring to convert the entire contents of the file into a string. So first off, before you tell me in the Zoom chats, I know, never use this, right? Never ever use source to begin with, and never download a file using this particular mechanism. But it's quite possibly the fastest way to download it in Java 8 using the Scala API. So forgive me for using it. Anyway, we can see here the source of the leak, right? Because we're opening a resource here. We're calling getlines, which is going to give us a lazy iterator. This iterator here that we get back from getlines is going to be lazy. And then we're turning that into a string. So we're opening something and then we're not closing it. So already we see a problem here. And that problem is caused by unsafe open. So unsafe open, it is returning a resource. And as a result, there is some possibility that whoever calls this function will acquire the resource but fail to release it. And we have ways of dealing with applications like this, which is virtually every application. You restart them at regular intervals. But it would be even better if we could build our applications in such a fashion that they would not leak resources. And in fact, we can. So one of the tools that functional programming gives us is the ability to describe resources using data types in a safe and sane fashion. And there are two benefits of doing this. First off, it allows us to identify where resources are so we know that. But it also, number two, it allows us to constrain the interface to that resource in such a fashion as to enable us to write good code without thinking. So if we describe this as a resource, then the interface around that will allow us to consume the resource, and after we've consumed it, it's gone. And we're going to, right now, we're going to refactor this. Actually, we won't refactor it. We're going to leave this the way it is because we don't want to break all the code out there. Instead, what we're going to do is introduce a new version of this open. It's not going to be unsafe open. We're going to make a so-called safe open. And this safe open is going to utilize a data type in Zio called managed. And managed takes two type parameters. First type parameter is an error type. So this is the type with which the resource, the acquisition of the resource might fail. So in this case, when we call open on this, it is quite possible that this throws an IO exception. And that could happen because, for example, the file doesn't exist, or because there was a network error of some type. But if something goes wrong, then what happens is when we open it, we're going to get back an IO exception. That's not the only point at which we could get back an IO exception. As we incrementally read the contents of that file, we could also get back an IO exception. But for now, let's just talk about this part. So in that case, we're looking at Java IO exception as being the error type parameter for managed. And then we'll still return a source. And note here that using managed has the following effect. First off, we know that this represents a resource because we're reflecting that in the return type of the method. Open gives us back a resource, a managed resource. We also know what this resource contains inside it. It's a source, which is Scala IO source. And we also know that acquiring that source could fail with an IO exception. So this is something that functional programming gives you, which is the ability to use the Scala compiler to help tell you more about the structure and runtime behavior of your program. We know here that this acquiring the source could fail with an IO exception, and we're using the Scala type system to tell us that and to track that for us. So in order to construct a managed, we actually need to use what's called a functional effect. And functional effects are built into ZEO and Monix and Cats.io and other libraries like them in the Scala ecosystem. And what they allow us to do is convert side effects like input-output operations into lazy descriptions of those operations. So that's what they do. They convert a side effect into a pure value, into a functional effect. That's a recurring theme of functional programming, is in functional programming, instead of doing things, we describe them. And these descriptions are ordinary values. They're pure values. They're immutable values. And we can reason about them in the same way we reason about Scala collections or Scala option or all the other wonderful immutable data types in Scala's standard library. So in order to construct one of these managed structures, we need two things. We need an effect that will succeed with the source and possibly fail with an IO exception. So I'm going to call that effect acquire. And you can create an effect with the ZEO constructor. And I'm going to wrap the following in here. I'm going to wrap actually unsafe open. I'm going to call that here. I'm going to call unsafe open with the slug and with the file. And then this is going to give me an effect. And I can hover over the type here if I want to see it. It's task is a type alias. This is going to give me an effect here. And the full type will be ZEO any IO exception and source. And this is the only effect type in ZEO. It's called ZEO and it has 3 type parameters. This, like we covered this morning, is what the effect requires. This effect doesn't require anything. If this is the type with which the effect could fail, this is the type with which the effect could succeed. Now, actually, this one's going to be throwable here. I want to make it IO exception. So this one here has a type that's too broad. I want to narrow that type. In order to narrow that type, I can call a method called refine to or die and just specify the exception type here. And that's going to take that throwable and say, no, I'm really only interested in the subset of throwables that are IO exception. And if it's some other one like null pointer exception or whatever, then I don't want to deal with that. I want to ignore that. I want to allow the thread that's running this code in effect to die. So this is my acquire effect. And then I need a function called, I'll call it release. And what this function does is it takes that source, which was acquired in this effect, and it returns an effect that releases it. So in this case, I just take the source and I call close on it. And this release effect here, you can see that it also fails for a throwable. But the contract of the constructor that I'm about to use for manage, let me just actually write that. You call manage.make and you specify the acquire and the release. And then it gives you back the resource inside this managed data structure. So you can think of a managed as being a combination of description of how to acquire the resource with a description of how to release it. And it's complaining right now because this release function here, it can fail for any throwable. However, in order to be well-defined and sensible, a finalizer should not be able to fail. So the Scala compiler is being my friend here and telling me that this release thing here could fail. And if it does, then the behavior of my program is poorly defined. So I have to basically decide how I'm going to handle that. If a finalizer fails, if the release of some resource is going to fail, this is equivalent to something that you would put in a finally block, for example, then what's going to happen here? And in my case, I'm just going to say or die. So I want the code running this to die in the event that closing this resource proves fatal. So then I make this managed resource and I return it from this function. Now what I've done here is, first off, I've made it impossible, well, not impossible, but rather extremely difficult to leak this source here because it's wrapped in managed, and managed has a very constrained API. Managed makes sure that when you use the source, it will be acquired safely and then released safely. So I've made it, if not impossible, then extremely difficult to leak source now. And now I can hand this managed source around to the rest of my code, and it never has to worry about opening and closing things. It can operate at a much higher level, a semantic level. It wants to deal with a source, and it can deal with the source and not have to deal with the messy problems involved in acquiring and releasing sources. And these managed resources, they compose very well. They compose together horizontally and vertically and in all sorts of very interesting ways. And in all cases, they won't leak resources. So managed is a tool from functional programming that allows us to build resource-safe applications without having to think about it. And I've also reflected the very real fact that this thing here can fail. When we go to acquire this, we can fail with an IO exception. And then finally, almost like tangentially to all these other benefits, I've actually turned open into a pure function, like we talked about this morning. Open now is a pure function. If you give it the same slug and the same file, you will get back the same managed source. Nothing is happening here other than building basically a description of how to acquire a source using this slug and this file. So if you call open with the same parameters, you get back the same description. So now open is a pure function, and I can use it the same as all my other pure functions. And that enables me to refactor. It has some testing benefits as well. And then also it enables me to actually write combinators on this thing, on the return value of here, which I don't need to do because it has plenty of combinators on it, has plenty of methods that are very useful and powerful and they'll allow you to compose and transform these things. But the point is that that's only possible because I am returning a description of how to acquire a resource. I'm not actually acquiring a resource here. So once we have this open, it is now trivial to define a safe download. So this unsafe download created the leak. It opened it, but it forgot to close it. So using managed, we're going to create a download that is going to give us back a ZO effect that does not need anything. It can fail with an IO exception, and it gives us back a string. And how we get here is we call open with this slug and this file, and then we call use. And we will be passed, inside use, we will be passed, the function that we pass to use will be passed the actual resource, which is in our case, a source. And inside use, we have to return another ZO effect that consumes the resource. So in our case, we want to do something very similar to this one here. It's going to call get lines and make string. So we're going to take all this code and we're going to stick it in a ZO effect. And then we're going to refine the error type as we did before to IO exception. And there we have it. We have a safe download function. This is purely functional. We can tell by looking at the type that it could fail with an IO exception and that it will succeed with a string. If you call this using the same parameters, you get back the same result. So now let's move over to COVID-19 service, because we drilled all the way down into this spot. We've got to reverse the process. And what we're going to do here is add a safe version of load. So look at this version of load. So this version of load says, give me the day, the month, the region, and the year, and I'll give you CSV. First off, we know that this signature here is not quite telling us the truth, actually, because it's not necessarily going to give us a CSV file. It could blow up with an exception. And also, we know that this thing here is procedural. This is not a function, because if we pass it the same parameters, it's going to go off and do side effects. It's going to do IO. It's not actually going to return us the same value. So we're going to fix both of these problems by adding a load function here. And I'm going to have to add some imports to this one. So this one's going to give us back a ZIO of, it won't require anything. It will fail with an IO exception, and it will succeed with a CSV file. So I'm going to have to import Java IO exception. And then I'm going to have to implement this down here. But it's actually pretty straightforward. I already have the implementation of the other one. So virtually the only thing that's going to change is I'm going to change this unsafe download into a download. And then I have to use that string I get back from that to construct the CSV file. But look what happens here. So download now is actually not giving me a CSV file. It gives me a ZIO effect that succeeds with a CSV file. So I actually can't wrap this in CSV from string because it would be receiving not a string, but an effect that succeeds with a string. So if you know anything about these functional effect systems, or if you've used Future before, then you know the way to solve this problem is to use for comprehensions. And in for comprehensions, it's like you use the val x equals whatever syntax, except you don't say val, and instead of equals, you use the backward arrow. That's how you access the success value of an effect, is you stuff it into a for comprehension, and instead of assigning it, you use this backward arrow, which compiles down to a flat map method on ZIO effect. But ignore that for now. Just think anytime you want to operate on values that are produced by effects, you just stick them in a for comprehension, and instead of using the equal sign, you use the backward arrow. So once we get access to the string that results from downloading this file, we're going to call CSV from string on that. And instead of calling return at the end with a for comprehension, you use the yield keyword. So I know that this is kind of strange looking syntax, especially if you've not seen it before, but it's actually relatively straightforward to translate between procedural syntax and this syntax. It takes some getting used to, and it is unfortunate. Honestly, this for comprehension syntax is a little dated and could use a refresh. But that said, it's not too painful to get to know the ins and outs of it and be very proficient at working in this style of coding. All right, so we download it from GitHub, and then we yield it in here, and we've created something that satisfied this type signature. So before we proceed, however, before we leave this file and go one step higher, I am going to teach you a feature of functional programming that has very ancient origins. So for a long time, people knew you could use FP to pass parameters down to parts of your code. And you do that using a data type. It's called a reader data type. We're not going to get into the details of that. But in ZIO, this feature is called ZIO environment. And ZIO environment, that's that first type parameter of the ZIO effect. That's this one here. So this ZIO effect here doesn't require anything. But what we're going to do inside the companion object of COVID-19 is we're going to create a helper function that accesses this interface from ZIO environment. So let me show you how to do that. Basically, the type signature will remain unchanged. The only part that's different is this any here is going to change from any to has COVID-19. And this has wrapper type, basically this says this ZIO effect requires something that has this interface inside it. Has is a data type that can be thought of as a map. So you can stick lots of interfaces into that map, as many as you want. And you'll see examples of that later. For now, don't worry about how it works. Just think of this as an environment that contains a COVID-19 interface. So you create one of these effects by using ZIO access M, and then you have to specify a function that takes the environment and returns some effect. So we're going to take this environment and we're going to access the COVID-19 service. In general, there might be many things inside the environment. So you have to call get and supply using a type parameter saying which one you want to access. But in this case, our environment just has one thing in it. So I'm going to call get without a type parameter. And Scala is smart enough to infer that I want the COVID-19 service. And then on that service, I'm going to call load, and I'm going to pass day and month and region and year. So there we have it. I've created what's called an accessor function that accesses the COVID-19 interface through ZIO environment. And we'll see that these accessor functions, even though they're not necessary, sometimes they can lead to nicer looking code. So now we're at the point where we have a load function that has no resource leaks. Assuming all of this code is working, it has no resource leaks. And it has no resource leaks because we fixed GitHub download. We consumed the resource inside this block, and managed itself took care to open the resource before this block was executed and to close it after it finished. So managed now is doing the heavy lifting of ensuring that our resources are opened and closed as appropriate. And this would happen not just with one file, but if we composed a bunch of these managed resources together, we would get back a managed resource that would open and close all of them in a sensible fashion. For example, if one of them failed, then the other ones would be shut down as well. So we've solved our resource leak problems by using this data type. We've also turned all of these download and open and load functions into pure functions that are now using the type system to accurately convey the fact that, first off, they actually do input-output, but also they might fail with an IO exception. So now let's go all the way back to the main function. And what we're going to do is, instead of modifying this in place, we are going to copy aggregate into a new main function. So let me do that. Stats collector 2. So this stats collector 2 is where we will set about utilizing our new leak-proof load function, which is going to fix that first problem that I mentioned. This is extending ZIO app. So this is the run function, and how we implement this run function is we have the command line arguments and we return an effect here, and we get the exit code from that effect based on whether it succeeds or fails. So I'm going to copy paste this aggregate in here, and we're going to make a number of changes. First off, though, I think I have to import a whole bunch of things. I have to import fp, min, csv, everything in there. And then I have to import Java time, everything in there. And then, okay, it looks like it's working now. All right, so here's the function that I'm going to modify. And this was the original function, which called unsafe load. I'm going to change this to be the safe load function. Let me just make that change here and see what breaks. Okay, so something broke as expected, right? This broke. CSV retain here, I get an error saying retain is not a member of ZIO effects. Well, that's because CSV here is not a CSV file anymore. Rather, it's a description of how to load a CSV file. It's an immutable value that describes the act of loading a CSV file. It's a functional effect. So I can't actually call CSV methods on this effect. Rather, I have to operate on the CSV file, which is produced by the effect. And to do that, I can call a function called map on effect. And map on effect allows me to change the value produced by that effect into some other value. And in this case, I want to change it from the old CSV file to the aggregated and sliced and chopped up and sorted CSV file. So I'm going to do that here by calling map on the output of this. I will be passed the success of this effect, which will be a CSV file. And I'm just going to take all this code and move it unchanged into the body of map. And some things, well, actually, I'm not going to call COVID. I'm going to actually call capital C. I'm going to call this helper function in there. And at this point, what I'm going to do is I'm going to change the type signature. And later I'll delete the type signature, but I want to show you actually what this function is going to return. What it's going to return is a ZIO effect. This ZIO effect will need something. Unlike the other examples that we've looked at so far, this ZIO effect will need something, any type of environment that has within it a COVID-19 service. And it can fail with an IO exception. So I'm going to need that up there. And it's going to produce, if it succeeds, it's going to produce a CSV file. All right, so there we are. And this is looking better. However, we've still got an error here. And that error is caused by the fact that we get back from mapping over this, we get back basically a list of effects. And so we can't use the CSV combine operator on two ZO effects. We need to operate on the list that's inside the effect. Actually, we right now we have a list of effects. And what we really want to do is, we don't want a list of effects, we want an effect that produces a list. And one way to think about this is we want to iterate over all of these days of the month, and we want to produce some effect for each one. And then we want to get back an effect that succeeds with a list of those results. So ZO has an operator. No, egal, no. The operator is not called traverse. The operator is called for each. Proper God-given name here, for each. And what this operator does is it allows us to iterate over this collection. So everything from 1 to the days in the month, we're going to iterate over that. And for each day, we're going to generate an effect. And then ZO for each will end up giving us we'll end up succeeding with a list of CSV files. So all of this code here, the result that we get out from this code will be a ZO effect that succeeds with a list of CSV files. So in order for us to reduce those CSV files, we need to operate on the value, the success value produced by for each. So to do that, we're going to map over here and we're going to call _.reduce, and we're just going to smash them all into one CSV file. So you can see here, we're iterating over all these, and for every day and month, we're going to load that. And in the process, we're going to return a ZO effect. And then we end up getting out of this whole for each loop, we get back an effect that succeeds with a list. And then we map over that success value, and we just sum up all those CSVs by reducing them into a single CSV file. And notice that this parameter is unused here, and that's because I'm actually accessing my dependency on this service. I'm accessing it through ZO environment using this helper function that I added to the COVID-19 companion object. So let's delete that, clean up this code, and there we have it. So Victor asks, what's the difference with traverse sequence? And the answer is that traverse from the type class can operate on any data structure and must, by contract, return the same type of structure that it accepts. Whereas ZO for each, it doesn't use any type classes. It accepts an iterable, and it always produces a list. So it's a bit different than traverse, actually. All right, so I've ported this function over here, and I have, at least in theory, solved my leaky problem, but I'm not able to run anything. This just contains sort of bogus code from before. So I have a few more things to port. Let's go ahead and look at that now. So I have print summary and aggregate and summarize. Let me go ahead and port these over into this stats collector too. And this is going to be very straightforward port. I'm going to delete the type signature here, which is something you see me do a lot of. I'm going to turn this into a for comprehension. And then I'm going to turn these print lines into putStir lines. PutStir line is a function built into ZO that takes a string and gives you an effect that describes printing that bit of text to the console. And then you have to use this weird syntax. Unfortunately, you have to use this weird syntax with for comprehensions to basically say, I don't care about the return value of putStir line because it's just going to be a unit value. That's what this effect succeeds with. It succeeds with a unit value. I don't need that. And then I'm going to change this one into putStir line as well. And I'm just going to return a unit here at the bottom. And then let's see. Okay, so this looks good. And then it's complaining because we changed the signature of aggregate. It doesn't accept this service anymore. So I'm just going to delete this. I'm going to delete the type signature of this one here. I'm going to turn this into a for comprehension. and yield unit here at the bottom. So the result, again, I'm just by sort of programmatically translating this into the syntax that I taught you about, where you're using these backward arrows, and then I'm going to change the print lines into put-stir lines. And so now at every step, these return effects, and these effects, I'm chaining them together sequentially by sticking them inside a for comprehension. So basically, I'm sequentially composing all these different effects inside this for comprehension to yield a final effect here. That's how functional programming works. We take values and we compose them using operators, or we transform them using operators. And in this case, we're composing a bunch of effects together sequentially to yield a final effect. So let's take a look at the type signatures here. So print summary gives us back a zero effect that requires a console. It cannot fail, and it succeeds with unit. So already, merely looking at this type signature, we can tell you a tremendous amount about the behavior of this function. We can tell you that it interacts with the console and that it cannot fail. That's what this second type parameter is. It cannot fail, in that if it succeeds, it will succeed with unit. So we know about its error behavior, and we know about its dependencies, merely looking at the type signature. Moreover, because this is a pure function, we can refactor calls to print summary with reckless abandon. To do inline variable and extract variable refactoring safely, you have to be operating on purely functional code. Otherwise, those refactoring operations are not safe. So they're safe with this. So we have more information, and refactoring is safe. Testing becomes easier. And then also, we're able to, because print summary doesn't actually perform any side effects, it just gives us back a value. We're able to call operators on that value to transform them and compose them. We're able to build custom control flow, custom combinators that do whatever we want. And that actually gives us a tremendous amount of power, which is something we're going to see later. Aggregate and summarize, the type signature of this one's pretty interesting. This one requires an environment that contains both the COVID-19 service and the console service. So this one contains two things. So Scala has totally inferred the type signature here, and it said that when you compose all these effects together, you get back an effect that requires two things: the COVID-19 service and the console service, and that can fail with an IO exception or succeed with unit. So we're getting pretty close here to having ported over all this logic. We just have a little bit down here at the bottom. So in this main function, we can see that these constructors, this is using basically constructor-based dependency management, which is the prevailing pattern in Scala code bases. And it's creating the GitHub service and feeding it to the COVID-19 service. And then it's creating the scheduler service to use down here. So what we're going to do is we're going to utilize a variation on the constructor dependency pattern. So what we're going to do is we're going to, one bad thing about constructors, one good thing about constructors is they're simple, everyone understands them, and almost everyone can use them. However, one bad thing about constructors is constructors are not values. And because constructors are not values, they don't have great composition properties. They don't have any composition properties. So Zio has a data type called zlayer that represents a constructor, but it's been enhanced in a couple of different ways. So zlayer has three type parameters: an input, an error type, and an output. And a zlayer is a type of constructor whose inputs are here and whose outputs are here, and which might fail along the way. However, it differs from instructors in a few very key ways that make it way more powerful than constructors, but it's the same idea as a constructor. So first off, this constructor is allowed to do things asynchronously. Sometimes it is useful to be able to build a service asynchronously using callbacks or whatever, and zlayers can be asynchronous, whereas ordinary constructors cannot be asynchronous. Second, zlayers can acquire resources. They can create thread pools, or they can establish database connection pools and do other types of things like that. And then also they can safely release them. And that functionality is powered by zmanaged, the data type we've already seen. So, and then the third category is, unlike constructors, Z layers compose. They actually compose two ways, vertically, and that's where you have one layer that sits on top of another one. You have like some business API that depends on some sort of HTTP client. So that's vertical composition. And so you can basically feed one layer into another one. You can feed the output of one constructor into the input of another one. But they also compose horizontally, which is I have this layer that builds something and this layer that builds something, and I compose them horizontally, and I get a layer that requires the input of both and produces the output. So they compose beautifully in those two ways, and that allows us to actually create entire application dependency graphs just by composing these layers together. And layers are values, so we can store them in vals, we can factor out duplication. We can even have like whole package objects or whatever that contain shared functionality for our application. So duplication and abstraction, all that is possible with Z layers because they are constructors made better. They're constructors on steroids. They're constructors, but as first-class values that we can compose. And then of course they can fail with errors, and ordinary constructors can do that as well. Even though you're not encouraged in the Java world, you're encouraged to never throw from a constructor, but it still happens occasionally. But it's no real difference. But in Z layer, it's considered a good thing, actually. It's not considered a bad thing to fail in the construction of a layer. It doesn't leave anything in a poorly defined state. So let's go into first GitHub. In the companion object of GitHub, we are going to construct a layer that does not require anything and that builds a GitHub service. And we're going to call that layer live, and it's going to have the following type: any, nothing, has of GitHub. And we construct such a simple layer by using zlayer.succeed, which takes this service here and bundles it up into a has, so into this collection of services. A has is a collection of services. It bundles it up into there. And we can see by looking at this type signature, this layer does not require anything. It cannot fail because constructing this cannot fail. And it will succeed with a collection that includes the GitHub inside it. Now let's do the same thing for the COVID-19 service. And this one is a little more interesting. So this is the existing constructor, and we don't need to modify it. Remember, ZLayer is just a better constructor. So if you're using constructors, it's compatible. ZLayers are compatible with constructors. What we're going to do is just add a layer for this constructor. And we're, again, going to call it live. This one's going to be a little more complicated because it's going to require the GitHub to be in the environment, the GitHub interface to be in the environment. It's still not going to be able to fail, and it's going to produce the COVID-19 service. So there's several ways we can build this, but the one that I'm going to choose is something called from function. And in from function, we specify the input, which is going to be this environment that contains a GitHub. And then it's going to produce the COVID-19 service out of that. And so here's our function. This will be the environment. And what we're going to do is call new live, and we'll call env, and we'll get out the GitHub service inside. So this gives us back a layer that it requires the GitHub interface, and it succeeds with the COVID-19 interface, and it cannot fail. Simple wrapper around our constructor. And so so good question, which is, what's the goal that I'm pursuing with the use of these layers? So with use of these layers, basically what I'm doing is I'm creating a way to declaratively express my application dependency graph in a way that does not involve any side effects, and in a way that whose behavior is entirely specified by static types. So this will allow me to look at and know that I built the right thing. And also down the road, it's going to be more useful when I refactor this. For example, if I refactor GitHub to use a connection pool, which is something I would probably want to do, I'm not going to have to change any code. Because, I'll have to change this code in here, but I won't have to change anything downstream. I can model that interaction, the acquisition of a certain pool of connections, and then the release of that pool inside a Z layer. So I have additional flexibility going down the road. But I suppose why I'm showing that to you here is because this style of code doesn't work easily with Zio. So I'm refactoring it basically to Zio best practices. to show you what it would look like if you were building a real application, even though there's no super compelling reason in this simple toy example to do it this way. All right, so I'm at the point where I think I can recreate the rest of this, and let me do that as follows. So basically, my app logic is here. This is an effect that's going to be executed in this main function. So what I have to do here is I have to use all of these pieces that I've put together in some sort of sensible fashion. And here's what I'm going to do. The first thing I'm going to do is I'm going to call this, and I'm going to store this in a val. So I'm going to call this on the month of April, which is what the original code did. If we look back here, you can see the original code called it on the month of April and scheduled it here once every minute. So let's go back here and do that. So we'll call this one ag. And let's look at that and see what the type is. The type is going to be, it's an effect that requires COVID-19 and console, could fail with IO exception and succeeds with unit. All right, so we want to take and run this effect every minute. And one of the ways that Zio provides us to do that with is a repeat method that is baked on effect. And how that looks like is you just call repeat here and you give it a schedule. And schedule is a value as well. So just like ag is a value, an immutable value that models performing this aggregation and summarization, this parameter here that we pass to the repeat method is a schedule value. And we construct those using schedule constructors, and we compose them using schedule operators. So what we would like to do is build a very simple schedule using a fixed spacing of 1 minute between repetitions. So this is how we construct such a simple schedule. I'm going to have to import one more thing here in order for this to compile. And now I've built the schedule, and now I can use the schedule here. So I took this effect and I called repeat on it with this schedule, and now I get back a new effect called scheduled, which will perform the effect of the original, but according to this schedule. This is one of the amazing powers that programming with values gives you. So when you switch over to functional Scala, you can build combinators like repeat, which can take values and return values. This is not something that you can do. You can't take a bunch of statements and repeat them in a loop, because a bunch of statements aren't a value. You can't pass a bunch of statements into a function and get them out from a function. You need a value to do that. And that's what functional effects give you, is they give you the ability to interact with the real world, but as a model, as a value that you run way later. You run it at the end of your world or whenever you have to at the entry points to your application, but they give you that model of interaction with the exterior world as an immutable value. So you can write very powerful combinators like repeat, which operate on that value to transform or compose them with other such values. So this gives us our scheduled effect, which has the effect of the original one, but is repeated on this schedule. And now what we want to do is we want to, according to the original, what we should do is we should just kick that off. So this is using the scheduler, and then it's waiting for a line of input to be read. So how we'll do that in this world is we'll call scheduled, and I'm going to call a method called fork on it. And fork gives back a new effect that basically kicks this one. It models the act of executing this effect on a different fiber. So Zio has a fiber-based concurrency system. Fibers can be thought of as threads. And with the fork operation, we're kicking this effect off onto a separate fiber that's running in the background. So we do that, and then we're going to wait for the user to enter a line of input. So we'll call getStirLine, which is the corresponding version of readLine. And this operator here, actually, let me not use that. That's what I would use if I were just doing it by myself. But let's just do it this way. We'll get a line of input, and then we'll yield unit. And there we have it. Well, almost, not quite. We've got an error, and this error is telling us that Zio, which calls our run function here, it actually does not know how to build a COVID-19 service. And right now, this effect, if you look at the type here, you can see it requires a console service, which is something Zio does know how to build, and a clock service, which is, again, something Zio knows how to build, but it also requires a COVID-19 service. And Zio doesn't know how to build one of those. So we've basically got to take this effect here, and we've got to give it what it needs that only we know how to construct. And we do that using a method called provide custom layer. And inside here, we're going to give it the layer that constructs the COVID-19 service. So that was called covid19.live. However, there's another problem. We provide custom layer here. COVID-19, it actually needs something. It needs the GitHub service. So we need to take the GitHub service and we need to feed it to the COVID-19 service. So we need to do vertical composition because this service depends on the other one. So we can do that using the arrow operator, which is github.live greater than. So this takes this one here. It's complaining I'm not using fiber. So let me just get rid of that. So we're taking the GitHub service and we're feeding it into this. And this is just an ordinary value. So if we see that this is being repeated in our application more than once, of course we can and should just factor this off into some sort of value. Oh, right, I need to move this down here. Or we could put this in a library of recipes for defining how to construct these things. Now, in test code, which would be the interesting part, I might choose not to construct a COVID-19 using this particular recipe. I might construct a test implementation of COVID-19, which does not, in fact, require any GitHub. So test code might use a totally different means of constructing what this program here requires. And indeed, if you run this little program in Zio test, you'll find that it constructs things like test console and test clock and test scheduler and test versions of all these things. So you don't actually have to interact with the real world in your unit tests, which is a best practice. All right, so let's see, a couple of questions here. So Z-layer based composition is not like the cake pattern at all, actually. So it's quite different. Zio environment pre-Z layer was more like mini cakes, basically, because you constructed classes that were subtypes of all these other ones. You don't do that anymore, and that's thanks to has. So has composes at the level of values rather than at the level of types, which is more convenient. Can you build a game using Zio? Yeah, so people have built ray tracers and probably games with Zio. You could build lots of things. Although, when you're doing functional programming, pure functional programming, and you want high performance, you have to be very careful because it's easy to over abstract. You have to be very certain which parts you're doing high level pure FP and which parts you're doing low level systems level programming in. All right, so let me continue. There's some other questions. I'll review them later, though. I want to make sure we have enough time. So here we have it. This is our assembled program. And you can see here, it's very clean and very compact. I actually made it as sort of large as I could just to make it more descriptive. But this is a very tiny program. This is smaller than the other program, and it does significantly more. It's also much more flexible. So you can see that in a few ways. First off, this program has no leaking problems. It has no problems leaking. And that's because we've used data types that enable us to ensure our programs are correct by construction. Also, not only are there no leaks, but we've been able to benefit from combinators that apply uniquely to values. And combinators can give us enormous expressive power in a small package. We take this effect and we produce a new effect that repeats it according to the specified schedule. All this is declarative and immutable and 100% testable. So we've gained here an enormous amount of power. It's not possible, certainly if you made this any more complicated, it would not be possible to solve this in fewer lines of code, in less effort, or in a more testable way using any other approach, Akka scheduler or scheduled executor or any of that stuff out there. Whatever you come up with using combinations of those technologies, it's not going to be as testable, it's not going to be as declarative, it's not going to be as compact as what this is. This is going to be a tiny amount of code to express very, very complex things and do so in a type safe and testable way. So we've gained a lot of things, even though we've really only fixed one problem at this point, we actually have gained quite a lot. And in the process of this modularization, we've retained a very easy ability to test this. So 100% of this could be tested. The old one couldn't be tested entirely because there were bits of it that were hard-coded. But now as we're calling getStirLine and printStirLine, and we're using clocks and all this other stuff, the other one, impossible to test. In this one, it comes for free. You write a Zio test here, and then you get to interact with test clock, you get to interact with test console, and you can provide a test implementation of COVID-19 that looks at test data. So this is 100% testable, just sort of full stack testability here that we've gotten more or less for free. So let's go back to that list though. We've done a good job at solving that one problem, but it took us a lot of time and effort to get there. So let me close all the things we don't need and go back to this little preview and see how we're doing. All right, the application leaks file descriptors and eventually stops working. And we fixed that problem by using managed. And we also encountered a lot of other benefits on the side that came from refactoring our code to be pure functions using functional effects. Now let's go on to the next one and we'll see how long it takes us to get here. Okay, if some days worth of data is missing, no statistics will ever be collected. So let's take a look at that one. All right, this happens because we're loading data, it doesn't exist presumably, and we get back 404 or some type of IO exception. So we can see that actually in the type. We can see that this IO exception, actually, Zio is fully inferable, so we can delete all of these type signatures, and I actually recommend doing that if you don't have a policy against it, because it means you can just change your code and not have to update any types. So now we can see that this one gets this IO exception from this load. So this is where we're picking up the IO exception. So this is where it's failing. Now, what if we wanted to say, by this requirement number 2, if we have trouble retrieving a day's worth of data, we shouldn't fail. Well, we could do that in a type-directed fashion. We could say, I don't want this to be able to fail. We could turn this into nothing and say, let's use the Scala compiler to tell us what we need to fix in order to make this be true. Right now, we've changed it into nothing. There are no values of type nothing in Scala. It's the bottom type. And to say that something will fail with a nothing is to say that it won't fail at all. If you have an either nothing or A, it's the A. It's a right of an A, because there are no values of type nothing. In the same way, you plug nothing into this error type parameter slot, and you get back an effect that can't fail. So we've said, this is what we want. Hey, Scala, we want an effect that can't fail. Help me make this happen. We can use the Scala compiler as our friend to reason about the error handling behavior of our program statically at compile time. So here we go. We can see that we're picking it up from this one right here. It should be nothing, but it is in fact IO exception. So we have this effect here. This is an effect. When we call load, we get back an effect. Actually, we call load and we map over that. So we get back an effect from the map that can fail. And we want an effect that cannot fail. Well, there's a fallback operator we can use in Zio called or else. And for or else, on the left-hand side is your first effect, the preferential effect, the one we want to execute. And on the right-hand side is the fallback effect. Well, in this case, what we're going to do is we're going to call Zio succeed to construct an effect that will always succeed with csv.empty. So this is an empty CSV file. Over here, this is an empty CSV file that we're sticking into a ZIO effect. This effect, if we look at its type, we can see here that this is equivalent to ZIO any nothing CSV. This is an effect that cannot fail. It will always succeed with a CSV file, well, an empty CSV file. So the Scala compiler has statically helped us prove that we have now eliminated the possibility for this to fail. How did that work? Well, it worked because the or else operator. Basically, if this fails, then the or else operator, which composes this effect with this effect, gives us an effect that fails for the right-hand side's reasons. And the right-hand side effect can't fail at all, so the composition of these two effects cannot fail. So hence, we have used the Scala compiler to help us prove that point number 2 here is satisfied. Now, if some days worth of data is missing, we'll still collect statistics. So I'm going to delete this type signature here. Actually, no, I'll keep it just so you can see, and so subsequent changes don't modify that. All right, so number 3, if the application is sensitive to transient, the application is sensitive to transient problems in the GitHub API. Well, this one is not so very hard to solve. And how we do that is I'm going to take this effect here, and I'm going to apply this technique that I told you was safe to do in functional programs, which is extract variable. I'm going to extract this into an effect called load. And I can do this without changing the meaning of my program. That's guaranteed because I'm dealing with pure functions here. So now I have this effect called load that I'm mapping over. But what I really want is I want to give the GitHub API a chance. If it fails, I want to try it a few more times before I give up entirely. And to do that, I'm going to call a method on effect called retry, which takes the schedule and gives me a new effect that retries the first one according to the specified schedule. So my schedule is going to be exponential, starting from 1 millisecond. And I'm going to cap that by using the schedule intersection operator with a schedule that recurs 100 times. So what I'm saying here is, now I'm going to delete the type signature. What I'm saying here is I want a schedule that behaves like an exponential schedule, starting from 1 millisecond and then going to 2 and then 4, then 8, then 16 and so forth. And also intersect that schedule with another schedule that will recur at most 100 times. So the intersection of these two schedules is a schedule that will follow this one's delay pattern, and it will terminate when either of these schedules decides to terminate. So this one will terminate first after 100 times. So the composed schedule here will terminate after 100 times. So now I'm going to try to interact with GitHub for a maximum of 100 attempts. And I'm going to use exponential fall off here, starting from 1 millisecond. So this gives me the behavior I want and knocks off this third point. Number 4, the application should download and aggregate data files in parallel. And we're running out of time, so we've got to go super quick. So what we're going to do is, to accomplish this, we're going to turn this for each operator into for each par. And for each par is the same for loop, effectful for loop, except in parallel. So right now this will execute all the days in parallel. So now we've parallelized all of this with well-defined error behavior driven by these static types. And then number 5, the application should support a timeout on file downloads so it doesn't hang forever. All right, so what should we do about there? Well, fortunately, there's an operator on ZIO effects called timeout that allows us to produce a new effect that performs the function of the original, but is capped to the specified amount of time. And it's called timeout. We can specify, what I will do here is, I'll call timeout. I'll do this. I will time out each individual file. So I'm going to time out this one here by let's say 30 seconds. And then let me just look and see. Okay, I need to specify an E1. So I'm just going to specify timeout fail. This exception here is not going to be used. This exception is not actually going to be used because of my failover. So maybe I'll just do a new error or something. It's not really important what this does. So when I timeout fail, I have to specify an error type that will be used in the event that this timeout is reached. So I specify timeout fail, and let's see. The final one is if the application is still downloading the files from a previous run, it should not start a new run. So that was a very subtle problem in the implementation of the first one, is that this scheduled executor would begin again, even if the preceding one was still running. And I actually accidentally solved that problem. I accidentally solved it because I switched over here to use schedule, and I repeated this at fixed spacing between them. So we're going to do 1 minute in between them. And if we wanted to, we could actually turn this to spaced, which would do basically exactly 1 minute in between launching. But if one was already proceeding to run previously, then this will not duplicate the effort of that one. So basically, you don't have the backlog or catch-up problems with spaced. We could choose either one here. Probably spaced would be more faithful to the original. So there we have it. We have managed to implement all of these. And as you can see, like really the hard work was refactoring so that everything was a function and everything was a value. That was the hard work. And that didn't take us too long, but it did take us a little bit of time. And we had to write some adapters here for dealing with some of this legacy code. And also we had to get a little more familiar with this weird syntax for writing sequential flows using functional effects, which is for comprehensions. And that does take a little while. It does take a little while, but the benefit that we got out of that was once we had done that work, then we were able to go through this list of bugs and features and just one after the other. They just fell like this. They were all super easy. And they were super easy, not by coincidence or chance. You know, you could put lots of different things in here. And even if they're very complicated and quite different than this set of bugs and challenges, more likely than not, it would be very simple to solve them. And what this simplicity comes down to is the fact that, first off, functional programming enables us not just to refactor into test, and all that's great. I mean, it's important to know that FP has your back when it comes to refactoring. It has your back when it comes to testing your code. But also beyond that, FP embeds more information into types. We saw that numerous times. We saw how many of our types to begin with were actually kind of lying. They were saying, give me these strings and I'll give you back a string. And that's not actually true. And also some of our types were incorrect by construction, or at least leaky by construction. When we return a resource, an open resource, then it's possible for someone to forget to close it, as often happens. So functional programming allowed us to take that information and to put it into the type system. And now looking at these types, we can tell whether or not these methods interact with the external world just by looking at them. We can also tell how they'll fail, if they'll fail, and how they'll fail. And we can also, we can take resources and other things like that, and we can give them types, and those types can have methods that ensure that we can't do bad things with them, that we can't forget to close things. And so what this does is FP actually enables Scala's strengths as a statically typed programming language to really shine. We are really benefiting from that. All of these features here today, they're turning the Scala compiler into your friend to help you to understand your code base using the help of your IDE. You can look at your types and you can know what's going on. And that's amazing. And furthermore, we actually leverage that in several places. Like when we went to go fix this next one, we changed the type first, And Scala showed us what was wrong and where we needed to fix it. And then we were able to prove statically, using the Scala compiler's help, that we fixed this without actually having to do any work. So these are tremendous benefits, and they're just a taste. We've seen also that when you move to pure functions and immutable values, then you get the ability to have operators that transform and compose. And you don't ordinarily, with a bunch of statements that are doing side effects, you don't have the ability to create operators that transform and compose because you're not working with values. But in functional programming, we only ever work with values. We're never doing anything. We're at most describing something. And that description comes in the form of an immutable value. And so we're able to build any operators we want to do repetition or parallelism or retrying or whatever. We saw many of those operators here. These operators, they take one immutable value and they transform it to another. They take two immutable values and they compose it into one immutable value. And these operators, they enable you to be extraordinarily productive. Like, these requirements here are not simple. If you try to solve this using futures or Java util concurrent, or dare I say it, even Kotlin coroutines or relatively fancy bit of infrastructure there, you're going to take a lot of time, and it's going to take you a lot of effort to verify that your solution is correct. But Scala gives us, Scala and functional programming working together in harmony, give us the tools that we need to write extraordinarily concise, type-safe solutions to very complicated problems. Solving all these problems in the span of a few minutes, I think that's amazing. And I think it's a small taste of what practicing functional programming in Scala can look like. When you not only pay attention to the functional side of things, and you're not only making everything out of immutable values and pure functions and all that good stuff, but when you also pay attention to the object-oriented side of things, like subtyping, like all that type inference that happened that we were able to benefit from, all of the inference of the intersection, all that stuff comes from paying attention to the object-oriented side of Scala and leveraging that. And we're still using constructors. You know, we didn't change that. We're still using constructor-based dependency management. We didn't change that. We just put values, type-safe composable values on top of that machinery to give us the ability to compose together the application graph for dependency management. And then also taking advantage of, the third thing that we're taking advantage of here is ergonomics. You know, we're trying to use functional programming in a way that's not so scary, that doesn't require several days of workshop, very super intensive material in order to get. There was no type classes here. There were no implicits. There was no jargon from category theory. I didn't mention monad. I think I managed to get through the entire thing without mentioning monad, and no higher kind of types. This is the type of functional code that you can bring in to your coworkers. You can show them. They can see that. And when you show them that you can be this productive, and when you show them that you can reason about your code statically at compile time and fix things very fast, and when you show them just how fun it can be to solve even very tricky problems in a principled way, then you're going to bring new converts on. And that's what's happening now. I'm very excited to see that in the functional Scala ecosystem. More and more people coming from the outside saying, hey, wow, that functional programming stuff, it looks pretty powerful. I'm going to try that. So I hope that we're concluded with the material more or less. I hope that this has been entertaining, and I hope that you are equipped now with sort of new ammunition. If you're already a believer in the power of functional programming, I hope you're equipped with new ammunition. If you're not a believer, if you've just toyed around with this FP stuff, I hope you can see that the reason to do functional programming is not necessarily because of purity or all these sort of ideological reasons. The reason to do it is because of practical benefits that you can take into your day job. Benefits like testability, benefits like refactorability, benefits like reasoning about your code at compile time, benefits like being very, very productive because you're able to use combinators that can make short work of very complex, challenging problems. I hope you're able to take all of that back into your day job and hopefully make a few more converts. Unlike my last presentation, I actually encourage you to try this at home. Please do try this at home. This and other, many other ways of writing functional Scala code, not just the ZO way, but many other ways of writing functional Scala code. They have this level of accessibility, and they have this sort of magical sweet spot for you invest just a little bit. You do have to invest some. I'm not going to deny that, but then you gain back so much. It's like the low-hanging fruit that you get for using the simple part of FP, which is really, really hard to beat in any other paradigm. So I think I'm going to very quickly go through questions here, but I want to thank you all again for those of you who will drop off for attending this talk, and then I'll turn it over to back to Signify.
Thanks so much, John. Yeah, whatever questions you have for John, feel free to ask them now, and then we can obviously hand back to us to kind of give them final closing.
Sounds great. Okay, so question, is there an equivalent of or else that allows fallback effect to access? Oh, that's catch-all. That's right. Can you use Zio with Play? Yes, and in fact, there are already libraries out there that let you integrate Zio with Play. And whether or not it would be worth it, that's personal preference. I have given a talk on how Zio effects compare with futures, and I think that talk is very favorable on the Zio side. Basically, if you hate futures, you still would probably love Zio because Zio improves a lot of the usability and ergonomics issues with futures and just is way more powerful. How is Zio behaving with Akka? Are they easily compatible? So yes, there's a lot of projects out there that have integrated Zio and Akka together. So you can use the two. You can even use Zio with Akka clusters, thanks to some great work that Pierre did, Ghost Dog PR. He did that on Zio. Error is fatal throwable? No. So I think what you mean by that is if you call or die, then basically that's a fatal. Zio makes the distinction between non-recoverable errors and recoverable errors. Recoverable errors occur in the type, and non-recoverable errors don't occur in the type. They're considered defects or just non-recoverable errors like Stack Overflow. And Zio basically encourages you to change that as you move up your application stack. You know, at the outer layers, you're going to have a lot of low-level, maybe exceptions reflected in your type signature. But then at some point, as you work your way up the stack, you're going to say, that's fatal. You know, I'm not going to deal with that. And so you're going to convert that over into a non-recoverable error. Other errors, you're going to translate into business errors. They're going to be domain errors. And so you might even move in some parts of your application, move from throwables up to sealed ADTs or whatever. Zio, you have a lot of flexibility, but basically that fundamental distinction between recoverable and non-recoverable errors is something that Zio embraces and I think leverages to good effect because it enables you to dynamically change that in depending on which part of your application you're in. Wouldn't it be better to use new exception for the timeout? Yeah, so probably new exception because that error might be considered fatal. Timeout exception would probably be the best one to use actually because it actually reflects the fact that it failed due to timeout. Do you unsafe run from your controllers? Yes, if you're using Play. Shouldn't the retry be after the timeout or the timeout before the retry? And that depends. So they mean different things. So if you retry, let me actually show you that real quick. So if you time out the retry, then you're timing out all of the retries, right? So no matter how many times you're retrying, you want this to succeed within this given bound of 30 seconds. Whereas if you do it before, then you're going to add the retry on top of that timeout. So it could be, you know, 30 seconds multiplied by 100, well, plus this spacing factor. I deliberately chose it this way because I want to get all my retries over with. Basically, I want to give up after 30 seconds. So that's why I did it this way. But you can see how you can achieve, because of the compositionality of these operators, you can achieve any possible semantic you want just by moving stuff around. It's just up to you to decide what makes sense for your business domain. What's the magic behind fork? I expect it when you use a fork comprehension like this, right? So fork takes this effect and kicks it off running. And the thing that you get back from fork is actually a fiber. And a fiber is something that you can interrupt or join. So I didn't do that because I don't need that fiber here. I just forked it off. But the key thing here is there's actually two fibers here. There's the so-called main fiber, which is executing this lines of the fork comprehension. And then At this point here, where this effect is forked off into a separate fiber, there's a second fiber. So now we have this fiber here that's running in the background forever until the app is terminated, at which point this one will be shut down automatically. So this fiber here is the single or the sole child fiber that's just off in the background doing its thing, running as long as necessary. Suggestion of a book or something to read to approach FP and functional effects. So I think there have been some out there that tackle that. There's FP for Mortals and a practical FP using Scala and several other ones that have some functional effects stuff in it. And also I would say look for an upcoming book on Zio by yours truly and Adam Fraser. Yeah, this one here is waiting for the user to enter a line of input, and then it will continue. But it's not going to do anything about this fiber. If you wanted, you could do something like this. You could hold on to a reference to this fiber, and then in the following line of code, you could call fiber interrupt to kill it. But that's actually not necessary in most cases, because Zio is very good about making sure fibers are shut down when they need to be. So for example, when this terminates, this fiber here will automatically be terminated, which is the correct behavior that you want in most cases. And if you don't want that behavior, you can call fork daemon, which will fork it off into a daemon fiber, which will not be supervised by its parent. All right.
Are you still going with the questions?
I think I'm almost done.
Oh, that's fine. Sorry, I can't see them my end, so I'm just checking.
Okay, it looks like there's a couple more. Do you have any ways to maintain decent performance with this, given that either T state monads are quite slow? So here's what I would say about this. First off, Zio does not use or encourage monad transformers, and that's because you don't need monad transformers. If you have 3 type parameters like Zio does, first off, there's a reason for 3 type parameters. Every program in the world, it needs 3 things in general. It needs a way to succeed. It needs a way to fail. So these are ways of bubbling up information higher to our program. So you need a way to fail and a way to succeed. That's just life, sort of. But also you need a way to propagate stuff down. So you need a way to bubble stuff up and a way to propagate stuff down. That's all you need. And if you have that, everything else you can get for free. So Zio has 3 type parameters precisely because every program needs those 3 things. And it makes sense to bake it in because then you can get the benefits of all the monad transformers without any runtime cost. When you bake an effect into the Zio effect type, then it comes for free. Whereas if you add it on top with a monad transformer, then it's extremely expensive. So every layer of your monad transformer stack will add about 4 times, it could be worse than that, but it will add about 4 times performance overhead in purely synthetic benchmarks. Whether or not those mean anything depends on your application and how much time it spends sort of in the glue versus doing bulk operations at a lower level. But nonetheless, people have observed that if they have deeply nested monad transformer stack and they're doing this style pervasively throughout their application, you will very, very significantly notice the performance drawbacks of monad transformers. And if you have either T and state T and reader T and option T and so forth, you can eliminate all of those with just Zio. So you eliminate either T because it has the error type. You eliminate state T because you can stick a reference to your state inside the environment. So that allows you to eliminate state T. You eliminate option T by using a unit for your error type or by using option of E for your error type if you want to combine either T and option T. So you can eliminate all of these monad transformers. 100% of all these monad transformers can be eliminated, and you can work with a totally flat type, which allows you to do it more performantly. But that said, you still have to, in high performance applications, you should make sure that you do batch work between the binds is a nice way to think it. Do it between the flat maps, because the flat maps is just always going to add overhead. And yes, we're going to get faster, you know, with Loom, we're going to get it faster. With Graal VM, we're already faster. But still, for a performance sensitive application, make sure you're doing bulk batch oriented work between the flat maps.